Okay, in the last video I did not finish my thoughts about example 4 here. Sorry about that, I got interrupted in the middle of doing it and I lost my train of thought. But this point, when we're talking of sales, the point where sales reach a maximum the point where sales reach a maximum, which for the original graph is the steepest slope, right? Sorry, not where sales rate. Sorry, that's a big difference. Where the sales rate reaches a maximum, that's going to be the steepest slope for the sales function. The maximum value for the derivative, because this is sales rate, right? This is sales rate, and this is sales acceleration. So the highest sales rate is where the slope is a maximum, or where S prime is its actual value is a maximum, or where the acceleration, the second derivative, is 0. The point where this happens, where sales rate reaches a maximum, is called the point of diminishing returns. You can no longer sell anymore for whatever reason. There's no way to increase the rate of your sales. Everyone has your product, or there's not enough demand, or whatever it may be. That point is called the point of diminishing returns. Alright, so let's keep going with the next thing, which is extrema test. Let me say homework. Basically, just all of the problems. Let's see, 1 through 13. 1 through 13 odd. Since these lectures can be so much longer now, 17 through 23 odd, I can do a lot more, and I can assign a lot more. 25 through 31 odd. So these are different sections of the homework. 33 through 37 odd. Now remember, these aren't for credit. The credit's coming from the WebAssign. And let's see a few of those application problems. So the credit is coming from WebAssign, but if you go look through these problems. You don't have to do every single one, but pick a few from each of these sections. I think each of these is a different section of material corresponding to one of these different topics. So go through, look at them, practice a few from each section, and you'll be just fine. Okay, so let's move to a new extrema test. So, the second derivative test. For relative extrema. The second derivative test for relative extrema. The first thing we need to know is where the graph is flat. Because if we know where a graph is flat, say we have some curve like this, if we know where it's flat here and here, then if we also know if it's concave down or concave up, then we can say whether this point is a relative max or a relative min. So we need to know, the first thing we need to know to use the second derivative test for relative extrema. Need to know where flat flat spots are. And that comes from setting first derivative equal to 0. And solving for x. Second thing you need to know about concavity at that point. Or at the points, possibly at the flat points. If you know it's flat, then you know it's an extrema point. Most of the time, right? They're not always. Remember, there are some times when you can have zero derivatives where it's not an extrema value. But, wow, I really butchered the spelling of that. That's supposed to say derivative, whatever. First derivative equal to 0. So the first derivative thing tells you, this tells you where they're flat, but it doesn't tell you if they're max or min. But if you know about the concavity at those points, right, if it's concave down, then that flat spot has to be a maximum, right? If second derivative is negative, like it would be here, then the point is a relative. It could be an absolute max. It could be an absolute max. That just depends on the graph itself, like the behavior of the graph. But it's definitely going to be at least a relative max. And if second derivative is positive, oh, I'm about to do it again, derivative is positive, then the point is a relative min, like this, right? Positive concavity, concave up, positive second derivative, that means that point is going to be a relative minimum. Okay. By the way, if the second derivative at that point is 0, then the test is inconclusive. It doesn't tell you anything at all. It doesn't tell you if it's a max, min, or anything. So if you get 0 for this test, if you're testing one of these points and the second derivative is just 0 at that point, then it doesn't tell you anything. Alright, number 1. Let's do some examples. F of x equals x squared minus 2x. Find relative extrema. Find the relative extrema. Okay, well first we need to find some candidates by setting the second derivative equal to 0. There's the second derivative, just using the power rule. We're going to set this equal to 0 and solve. X is 1. X is 1. Now we need the second derivative, but that's just going to be 2. Always positive, so I can't even really, I could plug in 1, but f of 1 would still just be 2, right? It's going to be 2, or sorry, f double prime of 1. There we go. For any x value, it's always going to be 2. It's always positive. So that means this is concave up, so that has to be a min. Because if it's concave up, if its second derivative is positive, that's concave up. Then that point that we're testing has to be a min. So, point, what is the point? X is the, 1 is the x value. What is the y value? Plug in 1 into the original function, we'll get 1 minus 2, so negative 1. So, 1 comma negative 1 is a relative min. Now, it might be, and in fact it is, an absolute min, but to know that it's also an absolute min, you would have to know what this graph looks like. All those other tests that we had in section 5.1 or 5.2, whatever it was, to test if it's actually an absolute min. All the second derivative test tells you if it's a max or a min relative to the points around it. It can't tell you about the behavior away from those points. But a point can be, technically all absolute max and mins are also relative max and mins, because if they're absolutely, say for a max, an absolute max, if it's absolutely bigger than every other point on the graph, then relative to the points around it, it's still bigger than those. So every relative max and relative min, or sorry, that's not right. Every absolute max and absolute min is also a relative max and relative min. Is that right? Yes, just by definition. Not the opposite, though. The opposite does not. So if you wanted to know if this was an absolute min, you would have to do some further testing with this. Basically, try to get a graph of that function. Let's do some more. Number 2. G of x is equal to x cubed minus 3x squared minus 9x. Okay, first we need our candidates for potential extrema, so let's set this derivative equal to 0. We got to get the derivative first. There it is. Set it equal to 0. Oh, this will be fun. It's quadratic. How do we solve this? Well, you got to factor. You can pull a 3 out of everything. Now factor it. It's got to be a 1 and a 3. Those are the only numbers that multiply to give negative 3. And in fact, it's got to be the 3 that's negative so that their sum will be negative 2. And that gives me 2 solutions. Negative 1 from this, and 3 from this. So I've got 2 flat spots. Now, is this one a relative max or min? Is this one a relative max or min? Well, all I have to do is find that second derivative, which will be taking the derivative of this, so I'll get 6x minus 6. And now I just plug these in to the second derivative. So g double prime of negative 1 is going to be negative 6 minus 6. That's definitely going to be negative. That's all I care about is the sign. Okay, what about g double prime of 3? That's definitely going to be positive. This means concave down. This means concave up. What does that mean for these points? What does that mean for these points? That means this one is occurring at it will be a relative max, and this one will be a relative min. But let's actually get the points. I need to know the y values for each of these points. G of negative 1 is going to be plugging negative 1 into this. That'll be plugging negative 1 into this. That'll be negative 1 minus 3 is negative 4 plus 9 will be 5. And then g of 3, 27 minus 27 minus 27 is going to be negative 27. So the points, well, the point negative 1 comma 5 is a relative max. And the point 3 comma negative 27, this one, is a relative min. Okay, one more. How about x to the 4th? Well, first derivative is going to be 4x cubed. Set this equal to 0 and solve for x. That's just going to be x equals 0. The 0 you'll divide by 4, cube root both sides. 0 is going to absorb all of that. So there it is. And get the second derivative. I think you might be able to see what's coming here. Plug 0 into this. We want to know the sign of this, right? But it's 0. So the test is inconclusive. Inconclusive. So if you wanted to see if this point is a relative max or min, you're going to need to know about the graph of the. You're going to need something else. You're going to need some all the other tests we did. You could test points around x equals 0 in the first derivative test. Best thing really though, is to just know what the graph looks like, right? That's roughly x to the fourth. So clearly that point is going to be a min. In fact, it would actually be absolute, wouldn't it? It would be absolute. But we could not figure that out from the second derivative test because we got an inconclusive result. I forgot to add some to the homework, 45 through 49 odd. It's really not as many as it looks, because they're all odd, so it's not too bad. I'm going to put these two topics together in one video because they're both pretty small. Higher order derivatives won't take long at all. Oh, where's my... Alright, so higher order derivatives. So we've only been talking about second order here. Well, first and second order. But you can take higher order derivatives. First, let's just talk about notation. When you've got f prime of x, that's the first derivative, then you've got f double prime, that's second, f triple prime, that would be the third derivative. Once you get beyond 3, you start using this notation, little parentheses and the number of derivatives you're taking up there, so the next one would be f raised to the fifth, but it's not a power, it's a number of derivatives, so the nth derivative would be whatever number of derivatives you're taking, so f, and then in this position where an exponent would be with parentheses. You need to have parentheses around it. That's how you denote that it's a derivative and not like an exponent or something like that. With the other notation, Leibniz notation, alright, what is going on here? Okay, that's the first derivative. The second derivative would be this. Third derivative would look like that. And then the nth derivative would be d to the n times f, and then dx to the n. Okay, let's practice taking some higher order derivatives. Let's say f of x equals x cubed minus x. Let's find f prime, f double prime, f triple prime, and let's go all the way up to, would it be possible for us to find the nth derivative? Well, let's, yeah, that's fine. That doesn't really, that wouldn't, I would have to tell you what n is. That's okay. Alright, first derivative, it's going to be 3x squared minus 1, just by the power rule. Second derivative, it's going to be, that one's going to go away, so it's just going to be 6x. Third derivative, it's just going to be 6. Fourth derivative, that's just going to be 0. In fact, what's the fifth derivative going to be? It's going to be 0. For the rest of these numbers, it's always going to be, for the rest of the derivatives, past 4 and beyond, it's just going to be 0. All polynomials are going to do this at some point. All polynomials, their powers are going to keep diminishing. 3, 2, 1, 0, that's their exponents. 3, 2, 1, 0, and then they just turn into just straight zeros. So the exponent of the x here, the variable x, is technically 0 here. And then it just, all the numbers completely disappear and it just stays constantly 0. What about e to the x? Well, g prime of x is e to the x. Yeah, I think you get the picture here. G double prime is just e to the x. So I could keep going all the way. Any derivatives, oops, any derivative will still just be e to the x, because e to the x doesn't change. More interesting maybe, what about e to the 2x? Because remember, by the chain rule, that 2 is going to drop every time you take a derivative. So the first one would be 2e to the 2x. Second one would be 4e to the 2x. Third one, 8, always dropping a 2. So what would it be for h of the nth derivative? Well, you're going to have, how many 2's are you going to have? Here you have 1 2, 2 2's, 3 2's, n 2's, all multiplied together. That's kind of interesting. What about something like k of x equals 3x plus 5 to the 4th power? Well, the first one, definitely going to be an application of chain rule here, with inner function and outer function being that power of 4. So there's the derivative of the outer with respect to the inner, times the derivative of the inner. So that's going to be 12 times 3x plus 5 all cubed. And then k double prime of x, taking the derivative of this, 36 times 3x plus 5 squared. That's the derivative of the outer with respect to the inner. So I dropped that 3. I went ahead and multiplied this 3 by that 12. And then I'm going to have another 3 from the derivative of the inner. I'm going to have another 3 from the derivative of the inner. So that's going to be, what is it? 108 times 3x plus 5. There's always going to be a times 3 coming out. Well, not always. Whoops, squared. At least until it completely goes to 0. Because this is a polynomial, so eventually it will go to 0. Drop the 2 down, so 2 times 108 will be 216 times 3x plus 5. That's the derivative of the outer with respect to the inner, times derivative of the inner. What is that? 648. Could distribute it. Kind of don't want to though, so let's just keep going. K to the fourth derivative of k will just be derivative of the outer. Maybe this does get a little weird. It's fine though. Derivative of the outer will just be derivative of the outer, this gets a little weird actually thinking of it like this, but remember that this exponent is 1 here. Maybe it would be better to just distribute this 648. Technically you would drop the 1, multiply it by the 648, take the power down by 1, making it 0. That's derivative of the outer with respect to the inner, and then times the derivative of that inner, so there's that 3 coming again. But remember, this is just 1. This all just kind of goes away, so I'm just going to be left with 648 times 3. That's all that's really going to be left. And what is that? Oh gosh, what is that? I don't want to do that in my head. 600 times 3 is 1800, and then it's going to be 24, and then that's going to be 120, 144, so 144, so 1944. And that's it, no x's, right, because this went away. So the next derivative and all the rest, 5 and beyond, the 5th derivative and beyond, will just be 0, because that's just a constant. They'll all equal 0. So that's how to take higher order derivatives. And I'll just talk for a minute about higher order derivatives. If they're polynomials, easy for the most part. Even if they're like polynomials, you know, with the chain rule, still not too bad. Exponential functions, you get some nice behavior. When you start dealing with rational functions too, actually have a pattern to them, but you saw before how bad some functions can get just by taking the second derivative. So sometimes these get pretty nasty, taking higher derivatives. For physical applications of higher derivatives, because first derivative is like a speed, right? Second is acceleration. Third is called jerk, which is like a measure of acceleration per time. It's called jerk. I'm sure that has applications in the real world. You know, they want to measure like in car crashes how fast the acceleration is stopping, because that affects how bad crashes are, car crashes. What else can I say? There's a really nice theorem in calculus called Taylor's theorem for series, which we're probably not gonna get into that, but basically says that any function with certain properties can be really well approximated by a string of its derivatives, which is a really interesting thing. So you can take a derivative, just a derivative of the function at a single point, and just learn about the entire function based off of that little tiny bit of data. And that's a really interesting thing that unfortunately we probably won't have time to get into. But higher order derivatives definitely do have applications. We just won't talk about them very much. That is the end of 5.3. So, let me know if you have questions. Type them in the little reply button under this discussion, or you can email me about them if you want. And make sure you try these homework problems, and keep an eye out for WebAssign being assigned for this section. All right.